Imagine you're standing in front of a machine that can look at a blurry photo and calmly say, "That's your friend." Or listen to a sentence you speak and instantly turn it into text. You can feel the magic in the result. But inside the machine, nothing that looks like magic. Just numbers multiplied and added over and over. Neural networks are the engine behind that trick. A way for computers to learn patterns the same way we do, by adjusting themselves after making mistakes. Here's the uncomfortable truth that makes neural networks so fascinating. They don't understand images or language the way humans do. They learn a maze of tiny decisions that, when stacked together, start to look like intelligence. And once you see how that maze is built, the black box becomes a lot less black. So let's open it. At the simplest level, a neural network is a set of connected units called neurons, arranged in layers. The first layer receives raw input, pixels, sound waves, stock prices, whatever you're feeding it. The last layer produces an output, maybe a label like, maybe a number like tomorrow's temperature, or maybe the next word in a sentence. Between those two ends are hidden layers, where the real work happens. Each neuron is a tiny calculator with a very boring job. Take some inputs, multiply each one by a weight, add them up, add a bias, then push the result through an activation function. Weights control how important each input is. Biases shift the neuron's tendency to fire, like a built-in preference. Activation functions add nonlinearity, meaning the network can learn curves and twists, not just straight-line rules. If that sounded abstract, picture a group of people voting on a decision. Each person listens to several friends, trusts some more than others, and has their own baseline mood. They add up influence, then decide yes or no. A single person's vote isn't impressive, but thousands of votes layered can create a surprisingly smart crowd. When you feed data into a network, it performs a forward pass. Information moves from the input layer to the output layer. Every neuron does its multiply, add, activate routine, passing its result onward as a new signal. By the time the data reaches the end, the network has made a prediction. Now comes the moment that separates a random guesser from a learner. We compare that prediction to reality. The difference is measured by a loss function. Basically, how wrong was I? If the network says dog, but the image is a cat, loss spikes. If it's right, loss is small. Think of loss as the sting you feel when you mess up. Neural networks need that sting. Without it, they have no direction. So how do they fix themselves? This is where training enters, and it's a two-step dance. Backpropagation calculates how to change each weight, and gradient descent actually makes the change. Backpropagation is like rewinding a movie of your prediction. Starting from the final error, it moves backward through the layers, asking a very specific question at each connection. How much did this weight contribute to the mistake? It computes gradients, the slope of the loss with respect to every weight and bias. A steep slope means this parameter matters a lot. Change it. A flat slope means this parameter barely affected the error. Once those gradients exist, gradient descent takes over. It nudges each weight in the direction that reduces loss, usually by a tiny amount called the learning rate. Do that across thousands or millions of examples, and the network slowly becomes less wrong. If you want a human analogy, imagine learning to shoot basketball free throws. You shoot, you miss left, you feel the error, you mentally trace back. Elbow too far out, wrist, flick too soft. That tracing back is backprop. Then you adjust your form a little and try again. That adjustment is gradient descent. Training is just repeating that loop until your body, or your network, internalizes the right micro movements. Let's make it concrete with a toy example. Say you're building a network to guess whether a house is expensive. Your inputs are simple: size, neighborhood score, and age. At first, the weights are random, so the model is basically guessing. It might treat age as super important and underweight neighborhood. You show it a real house, 2,000 square feet, great neighborhood, 30 years old, and yes, it's expensive. The network predicts not expensive. Loss shoots up. Backprop says the weight on neighborhood should be higher, size should matter more, age maybe less. Gradient descent nudges those weights just a little. Next example comes in, and the guess is slightly better. After thousands of houses, the weights settle into a sensible balance. Nothing mystical happened, just thousands of tiny corrections piling up, and the size of those corrections matters. If your learning rate is too high, training becomes chaos. Weights bounce around and never settle. Too low, and learning crawls, like trying to steer a ship with a toothbrush. Real systems often adjust the learning rate over time. Big steps early, careful steps later. Even then, you can hit snags like vanishing gradients, where very deep networks struggle to pass error signals backward, or exploding gradients, where updates get wildly unstable. Modern architectures and activation choices were partly invented to keep those gradients healthy. Now, why do multiple layers help? Because each layer can learn a different level of representation. In an image model, early layers might detect edges and simple textures. Next layers combine those edges into shapes like ears or wheels. Deeper layers combine shapes into full objects like faces or cars. The network isn't told, this is an ear. It discovers that certain patterns are useful to reduce loss, so it builds an ear detector on its own. In language models, early layers might focus on local grammar, later ones on meaning and long-range context. Again, no explicit instruction, just pressure from loss-pushing weights toward patterns that work. Here's a key misunderstood point. Neural networks don't store knowledge as rules. They store it as geometry. Every training example tweaks the shape of a high-dimensional landscape. The network learns to carve out regions. Inputs that look like cats fall into one valley, dogs in another, spam emails in another. Prediction is simply, which valley did you land in? That's why they can generalize. They don't memorize one cat photo, so thus they learn a region of catness. But generalization has a dark twin. Overfitting. If a network gets too complex or trains too long, it can start memorizing the training data's noise, performing brilliantly on what it has seen, and poorly on what it hasn't. It's like a student who aces practice questions, but panics on a new exam because they learned the answers, not the concept. And sometimes that brittleness shows up in weird ways. Researchers have found that a tiny human invisible change to an image can fool a network completely. A panda becomes a gibbon with high confidence after a sprinkle of noise. That doesn't mean neural nets are useless, it means they see the world through statistical lenses, not common sense. Their strengths are pattern-rich domains. Their weakness is the gap between patterns and reality. Closing that gap is one of the big frontiers in AI today. To fight overfitting, engineers use tricks like more data, dropout, NEMO, randomly turning neurons off during training, regularization, penalizing overly large weights, and validation tests to catch memorization early. You don't need to remember the bag of tricks. Just remember the principle. Learning means finding patterns that survive the future. Okay, so far we've described a basic feed-forward network, but once you grasp the core loop, forward pass, loss, backprop, update, you've basically understood the heart of modern AI. Convolutional neural networks add structure for images, reusing weights across space. Recurrent networks add loops for sequences. Transformers add attention to decide what to focus on. Different architectures, same learning engine, and that engine has already seeped into daily life. Neural nets help phones unlock with your face. Cars detect pedestrians. Doctors spot tumors in scans. Banks flag fraud. And recommendation systems guess what you'll watch next. In each case, the system isn't thinking like a human. It's matching patterns in data so reliably that the result feels like thought. Which brings us to a final, almost philosophical question. If neural networks are just math, why does it feel like they're alive? Maybe because learning itself is a kind of choreography, error, adjustment, repetition. You see that in babies learning to walk, in musicians practicing scales, in athletes refining timing. Neural networks compress that same cycle into a speed and scale that humans can't match. But the cycle is still the cycle. A model is only as good as the data it learns from. Feed it biased data, and it learns biased regions. Train it on the past, and it can struggle with a world that changes. So the magic always comes with responsibility. Let's go back to the machine at the start, the one that recognized a friend in a blurry photo. Now, you know what happened in the dark. Layers of tiny calculators, weights and biases shaping attention, activations bending logic past straight lines, a forward pass making a guess, a loss function judging that guess, backprop tracing, blame backward, gradient descent nudging the whole system forward, again and again until the maze of numbers lines up with the maze of reality. Neural networks aren't magic. They're the hard-earned result of learning from mistakes and so, which honestly is the most human thing a machine can do.